Imagine a ball held up in the air. When you drop it, the ball falls. Did you notice that the ball fell faster as time went on? Let's graph the ball's position as time goes on. Notice how the graph is curved. The curve shows that the ball's speed is increasing over time. You might have expected the graph to be a straight line down. If it actually was, the ball's fall would look like this. In this unrealistic situation where speed never changes, after the first second, the ball falls by 30 feet, another 30 feet after another second, and the same 30 feet after another second. Let's graph the ball's real fall again. After the first second here, the ball falls by 10 feet, but after another second, it falls by 30 feet, then 50 feet after another second. Each 1 second period, the ball falls by an increasing amount, showing that the ball speeds up. Going back to our unrealistic situation, the ball falls by a constant amount each second, meaning that it's not speeding up, causing its fall to look unnatural. All we've been doing is comparing average rates of change between the two graphs. Formally, rate of change is how much one quantity changes in relation to another quantity. Let's graph a linear function, f of x equals 2x. If we have 2 points in the line, A and B, the horizontal distance between the 2 points is the blue line, and the vertical distance between the 2 points is the green line. Delta just means a change in something and is represented with a triangle. It's why I've labeled our distances as delta x and delta y. Regarding the earlier definition of average rate of change, the rate of change is going to be how much y changes in relation to x. It's calculated as delta y over delta x and is represented by the slope of the orange line. Currently, the value of delta y is 2 and the value of delta x is 1. Delta y divided by delta x is 2, which means that for every increase in x, we increase by twice as much in y. If we made our change in x 2, our new change in y would then be 4. Notice how our rate of change is still 2. This is because the graph is linear. No matter where our 2 points are on the graph, the change in y will always be double our change in x, so our rate of change stays the same. What would happen to our rate of change if our graph wasn't linear though? Let's graph the quadratic function f of x equals x squared. We'll have 2 points on the graph again, A and B. Here's our delta x and y like last time. And an orange line representing slope between the 2 points. This time the orange line was extended out so that we could see slope more clearly. Remember that the slope of the orange line is calculated as delta y over delta x. Here's the values of the same things we looked at last time. When we move point B to the right, the ratio of delta y and delta x gets bigger, so the slope between the 2 points gets steeper. Slope gets steeper and steeper the farther we move point B to the right. If point B is under point A, rate of change will be negative, which gets more extreme the farther we move the points. The rate of change formula that we have been using is delta y over delta x. Since delta just means difference between the 2 points, we can get delta y and delta x by subtracting a from b. And we can also get our y values from the function at x. What if we want to find the rate of change at a certain point? Let's look at the same graph of x squared again. At point A, we can see that its slope will be horizontal, but how could we prove that? Let's bring in another point, B, and measure the average rate of change between the 2 points like normal. Look what happens when B gets closer to A. The slope between the 2 points gets closer to the real slope of A, the white line. But if we move b on top of a and make the distance between the 2 points 0, we can't calculate rate of change anymore because we'd be dividing by 0, which is not possible. If we want to get a more accurate slope without dividing by 0, we can use the limit on the rate of change formula, which means that we are now making the difference in x as close to 0 as possible without making it 0. Let's apply this limit definition here. The distance between the 2 points is as small as it could be, and now our slope is 0, as we expected earlier. Let's try this at another point, located at x equals 0.5. We know that the slope here is positive, but we don't know its exact value. As point B gets extremely close to point A, our slope is 1, which matches up with our estimated slope at point A. We've been thinking of instantaneous rate of change as when the gap between the 2 points, delta x, approaches 0. We could rewrite this ratio by expanding the deltas and getting our y values from the function at x, like we did last time. We could also rewrite delta x approaching 0 to be the x value of b approaching the x value of a. These formulas are known as the limit definition of the derivative. Let's go back to our situation from earlier. We know that the ball speeds up while falling. Using what we just learned, we can find the speed of a ball at a certain time. Note that speed is just slope on a position time graph like this one. Here's the same graph of the ball's position over time. To find the ball's speed after 1 second, which is point A, we bring out the second point, B, move it very close to the first point, and then measure the slope between the 2 points. At the first second, the ball is falling at a rate of 20 feet per second. At this later time, using the same process, the speed is 32 feet per second. Here we are putting B before A, but the process still works. To conclude, here's the derivative of the ball's fall graphed in real time.